Welcome back to the Explainer. Today, we're going to tackle a huge concept in calculus, continuity. Now, I know it sounds simple on the surface, but really getting what it means, well, that unlocks some of the most powerful tools in all of mathematics.
So let's start with a really basic question. What does it mean for something to be uninterrupted? You know, a process that happens without any sudden stops or gaps or weird jumps. Maybe you're thinking about how your height changes as you grow or the path a ball makes when you throw it. It's just a smooth, unbroken flow.
Right. In the world of math, we call that whole idea of being uninterrupted continuity. And you've probably heard the classic way to think about it. If you can draw a function's graph from start to finish without ever lifting your pen off the paper, then hey, that function is continuous. It's all one connected piece. Simple enough, right?
Well, that pen analogy is great, but it only takes us so far. The real muscle of a mathematical definition comes from how it deals with all the messy, tricky cases. So, what happens when a graph doesn't play by the rules?
Because what if you're drawing that line and you're forced to lift your pen because there's a break in the graph? You've just hit something called a discontinuity. And it turns out graphs can break in a few very specific, kind of predictable ways.
These breaks, these discontinuities, they really come in three main flavors. First, you've got a hole. That's where a single point is just gone. Poof! Then there's a jump, where the graph literally stops at one level and then picks back up at a totally different one. And finally, you can have a misplaced point. The point is there, it exists, but it's floating somewhere off the curve where it just doesn't belong.
Okay, so to really nail down these breaks, we need something a little more powerful than just our pen analogy. I mean, it's a great starting point, but it isn't precise enough. What is a hole, mathematically? How do you define a jump? To build tools that work every time, mathematicians needed a super rigorous definition that acts like a diagnostic test.
And here's the core idea. For a function to be continuous at a specific point, let's call it a, there can't be any surprises. The value the graph is heading towards as you get closer and closer to a has to be the exact same value as the graph right at a. The approach has to match the arrival, no last-second plot twists.
This all boils down to a super handy three-step checklist. Number one, the point has to actually exist. If f of a isn't defined, you've got a hole. Easy. Number two, the limit has to exist. That means the function has to be heading to the same spot from both the left and the right. If not, that's your jump. And number three, the most important one. The limit has to equal the actual point's value. If they don't match, you've got that weird misplaced point. A function has to pass all three of these checks to earn the title continuous.
Now, this might sound like we're just getting lost in abstract rules, but I promise this property of continuity is literally everywhere. It's the language we use to describe all sorts of physical things that happen smoothly and predictably.
Just think about the world for a second. Your height doesn't just suddenly jump 3 inches in an instant. A car's speed changes smoothly when it speeds up or slows down. The arc of a thrown ball is unbroken. As a balloon inflates, its volume grows without any gaps. These are all perfect real-world examples of continuous functions in action.
And now we get to the really big payoff. See, knowing a function is continuous isn't just a fun fact. It's like a VIP pass that gets you access to one of the most important theorems in all of calculus.
This is it. The Intermediate Value Theorem, or IVT for short. And what it says is, if you have a continuous function between 2 points, it absolutely cannot skip any of the values in between. To get from its starting height to its ending height, it has to hit every single possible height along the way.
Here's a great way to picture it. Imagine drawing a horizontal line anywhere between where the function starts and where it ends. Because the function is continuous, because you can't lift that pen, remember? The graph has no choice but to cross that line. It can't magically teleport over it.
And that's really the heart of it. If you're driving your car from sea level up to the top of a 500-foot hill and your path is continuous, you know for a fact that at some point you had to be at an elevation of 100 feet and 250 feet and 499 feet. You have to pass through all those intermediate values. It's unavoidable.
So why is this such a big deal? Because this isn't just a neat observation, it's a rock-solid guarantee. And in math, and especially in science and engineering, guarantees are worth their weight in gold.
And here's just how powerful it is. Let's say you have a continuous function that's negative at one point and then it's positive at another point. Well, the IVT guarantees that somewhere in between that function had to cross zero.
That means a root is guaranteed to exist in there. We might not know its exact address, but we know for a fact that it's in the neighborhood.
And that's exactly why this is such a vital tool. Engineers and scientists use this principle constantly to prove that solutions to their incredibly complex problems have to exist. That's often the most critical first step before they even begin to try and find them.
So if you take one thing away from this, let it be this. Continuity is so much more than just drawing pretty smooth lines. It's a fundamental property that guarantees predictable behavior. It unlocks these amazing predictive tools like the intermediate value theorem that let us prove things with absolute certainty.
But that leaves us with one last little puzzle to chew on. We know continuous functions can't have breaks or gaps. But what about a sharp corner? Like the point of a V shape. You can definitely draw that without lifting your pen, so it's continuous. But would you call it smooth? That's a good question. And it leads us right to the next giant idea in calculus, differentiation. But that's a story for another explainer.